Hi folks, we're going to take a look at page 260, number 7. So what they want us to do here is to prove that this function is always increasing on the interval from negative pi over 2 to pi over 2, not including the endpoints. All right, so here it makes sense to work with the first derivative because we know that if we can show that the first derivative is positive on this interval, then it means the function must be increasing there. All right, so let me start by taking the derivative of that function. So derivative of secant x is just secant x tan x plus, take the derivative of tan x is just secant squared x. All right. And again, we see that relationship between secant and tangent in terms of their derivatives. And what I need to show is that this is positive on this interval here. Now, what I would suggest at this point is to turn everything back into sine and cosine because we have a lot more experience solving equations and working with sine and cosine. So let's see what happens here. So we've got 1 over cos x times sine x over cos x plus 1 over cos squared x. And actually that works out pretty nicely because we have sine x over cos squared x plus 1 over cos squared x. So same denominator, I can just add very easily. All right. So I notice that the denominator is always positive as long as cos x is not 0. Okay. But let's take a look at the interval that we're working with. So we know that cos x, okay, is 0 at negative pi over 2 and at pi over 2. Okay, but not in between. All right, so I don't have to worry about the denominator being equal to 0 because cos x is never 0 in that interval since we're not including the endpoints. All right, and it's being squared, so I don't even need to worry about what the actual sine of cos x is in that interval. All right, now for sine x plus 1, so here I can just, this is just a known fact, we can say cos x not equal to 0 on negative pi over 2 to pi over 2. By the way, you're noticing that I'm being very precise about what I'm doing because they are saying prove. They're not just saying show or show that it's reasonable that this is the case. We want to prove it. So we know that the denominator is not equal to 0. And of course, anything that you square that's not equal to 0 will be greater than 0 on this interval. All right, so we've taken care of the denominator, always positive. Now let's take a look at the numerator. Now, again, we can take a more intuitive approach here and think about the function, sine x, okay? And what am I doing? I'm doing sine x plus 1, so I'm just bringing it upwards. So what would this function look like? Well, it would just look like this. All right, so I see unless sine x is equal to negative 1, this sine x plus 1 will always be greater than 0. And of course, we know that sine x can only be equal to negative 1 at places like negative pi over 2 and 3 pi over 2. But again, it does say prove, so let's actually solve this out. So how would I show that sine x plus 1 is positive on this interval? Well, let's determine where it could change sign. So let's figure out where sine x plus 1 is equal to 0. We know sine x plus 1 exists everywhere, so I don't need to worry about testing where it doesn't exist. So here, sine x equal to negative 1. And so that happens at, well, 3 pi over 2, okay, which is already outside of my interval. So there's no point in going further to the right. So let's go to the left. Well, 3 pi over 2 minus 2 pi. So 3 pi over 2 minus 4 pi over 2 was, as we said earlier, at negative pi over 2. Okay, which again is not in this interval. All right, so the only place that sine x plus 1 could change sign in the vicinity of this interval is that 3 pi over 2 negative pi over 2. All right, that means that whatever sine x plus 1 is going to have, it's going to be consistent throughout this whole interval because this interval does not contain any zeros of that function. So all I have to do is test one value. Let me test 0, and let's see what happens. Well, sine of 0 plus 1 is equal to, well, sine of 0 is equal to 0 plus 1 is 1, so it's positive. So that means sine x plus 1 has to be positive on this whole interval. Okay, therefore, y prime is greater than 0 since both numerator and denominator are greater than 0 on negative pi over 2 to pi over 2. Okay, hence y is increasing on negative pi over 2 to pi over 2. All right, so just to recap, in order to show that it was always increasing, I needed to show that the derivative was positive. So I started by taking the derivative and simplifying it to more manageable uh, uh, format. Denominator, very easy to show that it's never equal to 0 in that interval, and because it's squared will always be positive. In order to show that sine x plus 1 was always positive, I tried to determine if there were any x-intercepts in the interval of interest. It turns out that they weren't, meaning sine x plus 1 has to have the same sign throughout the whole interval. So it was only necessary to check it at one value. And we determined that it was indeed positive, hence numerator and denominator both positive, and so the function is increasing on that interval. Okay, that's it for this one.